little bit of ways, it's March 5th. But 90% of that test is non-calculator. So the more you use the calculator now, the harder it is to take the test. And I tried to get you guys on the quiz, which I'll get back to you tomorrow. But that quiz on Tuesday, I tried to get you to not use the calculator, but some of you still use the calculator for that graphing. Like it really is a no calculator test, except for 3 problems. So the easier it will be if you stop using it now, unless it absolutely says to use the calculator. Sam?
Is that the grade version?
It is. I put it in this morning. By 8 o'clock, they were in.
Wait, which grade? That's it.
The quiz that you took on Tuesday.
Oh, that's it?
Yes.
Can we check?
Yeah.
Yeah.
I was feeling kind of good on that myself. Yeah, you did it okay.
But I'll give them back to you tomorrow.
Oh, no, what's 36 That's what my grade is.
Miss?
Oh.
Wait, it's quiz 7.1 to 7.3? Yep.
So you would use
What'd you get?
Ethan.
42 out of 45.
Oh, Ethan. 18.
Mine like isn't.
Ethan, what'd you get?
Oh, 42 out of 45. You're about the same. That was a really bad one. Yeah. Look at page 1.
Okay. So on in your packet on page 16, please. If you look halfway down, it talks about inverse functions. So we ended yesterday by just like plugging into the calculator with the common log base 10 and the natural log with the base e. So today we're going to try and look at inverses. We'll try and create an inverse function, but also use the properties of inverses to help us simplify. So it says, by definition of a logarithm, it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x. So they are inverses of each other as long as the base matches. We can pretty much say that they would be inverses. But I want you to remember a little bit about inverses before we actually start working through the problems. So when we showed or verified, confirmed that functions were inverses in chapter 6, we showed that f of g of x was equal to something, and g of f of x was supposed to be equal to that same value. What are they supposed to equal? F of g of x, g of f of x. Lisa?
Say G of F.
Not g of f of x. They're supposed to like simplify and break down to something. Okay? It's just x. So f of g of x is just supposed to equal x if we take the one function and substitute it into the other. That's called the composition of functions that we did last chapter. And flipping it around, taking g of f of x, that's also supposed to equal x. So we're going to do a little like verification to show that that's true for this inverse function. So we're going to use g of f of x and f of g of x, and just try and show that it works for inverse functions and exponential functions as well. So we're going to start with the f of g of x. So a composite function, remember you take the inside, you start with the inside, and I'll just write the inside down. That's the log base b of x. And you're supposed to take that and plug it in to the other function in place of x. Well, my f function is right here. And that f function says b, and in place of x, you're going to put log base b of x. So now I have the base and the log with that same base. They're the same. When that happens, because they're inverses, it's just like multiplication and division. They literally cancel each other out. So it's like x squared taking the square root of x squared. My base has an exponent that has the log with that same base. So that cancels, and it just gives you x. So essentially, the base and the log are canceling, and whatever the x is there is what your solution is, or what it's going to reduce down to. So this part right here is a property that we're going to use to simplify equations, or to simplify logs. So that would be one of the properties that we'll use to help us simplify the logs. The other property would be flipping it, so working with g of f of x. So working through the same way. You take out the middle function, the inside function, replace it, so f of x is v to the x, so we're replacing f of x. And then in the g equation, which is the log, instead of this x, we're replacing it with whatever's in the parentheses. Well, that happens to be v to the x. So just like the one above, if the log with a base b and the base of the exponent are the same, so the key is they have to be the same. So you have to have the same number as your base and the same number with your exponent. Then these guys cancel and again just equal x. So this is the other property that we'll look at and use. So there are two properties of logs, properties of exponents. So essentially in a log and an exponent like undoes itself. Just like if I had x squared and we took the square root of it, that cancels the x squared out because they're like opposites of each other, they're inverses of each other. So it's the same fact, but now we're using logs and exponents with the fact instead of squares and square roots. So the two problems underneath here, there's a handful of problems that start like that 29 to, maybe 29 to 35, like there's a couple there, that are going to be similar to this next example. So it says to simplify the following expressions. Anytime it says simplify, our goal is to break it down as far as you can go. So we have 10, and then the log of 6.7. So that follows this form right here, the one above, because you have a base with an exponent. So I have a base with an exponent. But the thing that we don't know right now that's not listed is what's the base of the log, because there's not a base written here. And for this to work, the base of the exponent and the base of the log have to be the same. So if it's not written, what is that base? Virginia? It's 10. So really, there's an invisible 10 sitting there. Even though it's not there, it's assumed to be there. And that's the tricky part. Because you're not used to seeing logs to begin with. But if you have an x plus 3, there's assumed to be a 1 in front of that x, even though we don't write a 1. Because it's like you just don't write a 1. It's not something you do when you have an x. That's the same thing with logs. So if you see a log without a little base, that log really has a base of 10. So because my base here is 10, and the log of the base is also 10, this is just equal to 6.7. Whatever that x is what it simplifies to, because it matches the property of inverses. So there's not really work that you have to do, you just have to notice that it's matching your property that you're given. So that's the one property with inverses of exponents and logs, and that's this first one up here. So if you have an exponent, as long as the base of the exponent, the base of the log are the same, they cancel and it's just that 6.7. Questions, because it's weird. The second one starts in log form, so that's going to kind of be like this down here. It starts out as a log. We have log base 2 of 16 to the x. So right here we have log base b of b to the x. So the number 2 and the number 16 are supposed to match up in order for this property to work. But they don't. One's a 2 and one's a 16. They're different. So we need to try and make it work for us. And if you look at the number 16, how else can you write the number 16? So think of the different ways we could write it, Maddie.
4 squared.
4 squared, so 16 is 4 squared. How else can we write 16 besides 4 squared? Sarah? 2 to the 4th. So 16 is 4 squared. 16 is also 2 to the 4th. Both of them work. However, which one of those matches with our base that we have in the problem? Sam?
Is it 2 to the 4? No. It's 4 squared. Where is it?
So if the base is 2,
Uh-huh.
we want to use the
You
fact
wanna
that
use-
16 is 2 to the 4th. Come on, so frustrating. So we're going to take out the 16, we're going to replace it with 2 to the 4th because it means the same thing. But now my bases match up. Now that 16 had an exponent of x, so that means 2 is going to have the exponent of 4x. That x just stays with the 4. They're now being multiplied together. So this is just answer equal to, you were saying, what was it, 90? Somebody else talking? It's just equal to 4x. Sorry. My base and this base match. So when they match, the answer is just that exponent of 4x because they cancel each other out. If they don't match, you have to force it to make it work. So we just had to change the 16 to make that value work. Questions? Yeah, that's weird. The next group of problems underneath say that you're supposed to solve the equation without a calculator. So we're not going to use a calculator. And I mean, really, based off where the x is in most of them, you can't use a calculator anyway. So in order for us to solve the equation, thinking about the exponent, thinking about the log form, just going to write them up here again. These two forms, going back and forth converting, you're going to use a lot for the rest of the chapter. So you're going to have them memorized as to how they're supposed to look when you're taking one and trying to put it in the other form. So if you look at A, which really should be 1, apparently I started counting with letters and then I decided that I'd rather use numbers. I don't know. It goes from A and then to 2. Yeah. I am like the most patient person, but I have no patience for Apple TV. Okay, good enough. So we have log base x of 81 equals 2. It's currently in log form, and without a calculator, even with a calculator, we couldn't really do anything with it in log form. So how could you change it to exponential form, which is something that we know how to work with? How could we write it as an exponent? Kate?
Do it, write it as x squared equals 81.
So we could change it, take the base, which is x, that gets the exponent of 2, and that's equal to 81. So if I solve that little equation, x squared equals 81, x is 9. It's only positive 9, because by definition, that base has to be positive. That's by the definition of a logarithm. So x is equal to 9. So that means I would have log base 9 of 81 equals 2, which is a true statement, because 9 squared is 81. So if you look at number 2, log base 3 of x equals 3. Virginia, how would you rewrite it? So she said x is equal to 3 cubed. You could have also said 3 cubed equals x. Either way is fine. And Virginia, what is 3 cubed? 27. So x is equal to 27. 27 is 3 cubed. So looking at number 3, log base 2 of 8 equals x. Aaron, how would we rewrite number 3?
2 to the x power equals 8.
Yeah, what power of 2 gives us 8? 3. And then the last one here, log base x of 64 equals 3. Mason, how would we rewrite that?
4 equals x.
And
X equals
x is 4, because the cube root of 64 is 4. So those are, I think, a little easier to kind of do because you're not really using that inverse fact. We're just trying to rewrite it in its opposite form and solve for x. Questions? So at the bottom of this page, there's one other thing to talk about with inverses algebraically, and then we're going to try and graph. So this one, the last 2 questions here, want you to find the inverse of the function. So when we talked about inverses, what did you have to do to find an inverse? Back in chapter 6. Is it?
Switch the variables.
Switch the variables, because if it's an inverse, it's supposed to be the opposite. Multiplication is the opposite of division. Adding is the opposite of subtraction. So if I have an x and a y and we want to find the opposite, we can switch that x and y. So now it's x equals log base 3 halves of y. So that's the first step. Switch it. Do the opposite. Flip your x and y. So the inverse is supposed to be an exponent because we currently have a log. How could I write this in exponential form? So what would it look like as an exponent? We've got x equals log base 3/2 of y. So exactly like we just did for these last 4 problems, we flipped them. So we switched the way they were written. Apparently I shouldn't have switched screens. So Paige, how would you switch it? About 3/2.
Oh, 3/2.
Yeah.
The exponent.
And then to the x. So you're looking at log base b. These are the forms. So the base gets my exponent, well, the base gets the exponent, and then that would be equal to y. So the last thing to show that it's an inverse, either use the f(-1) of x, so my inverse is 3/2 to the x, or you could say, because it didn't start with f of x, you could say y(-1) of x. Either one of those work, but make sure you're using inverse notation. So switch x and y, write it as an inverse. Write it as an exponent because that would be its inverse. So looking at letter B, if we follow that same process, switch x and y. That's the first step. And then based off of what we did over there, we then took it and wrote it as an exponent. But this doesn't have a base because it just says ln, where over here this had log base 3/2. Anybody remember what the base of it is?
E.
E, yeah, the base is E. So even though it's not there, it's invisible. It really is sitting there. There we go. So that E is invisible, but it really is sitting there. Sam, can you write this as an exponent then?
Good.
So what's the base? E. The exponent of the E is now and that's equal to
That's equal to
minus
4.
4. Yeah. How would you solve it, Sam?
You get y by itself.
Get y by
So
itself.
it would be e to the x minus 4
So close.
plus 4.
Plus 4, yeah. So e to the x plus 4 is equal to y. So inverse notation, either use f(-1) of x or the y with the -1. So e to the x and then plus 4. Questions? So if there's a log written and it doesn't have a base, the base is really 10. So it just says log without a base, it's really 10. If you have ln, that's the natural log, the base is really an e. You can place an e there so that it helps you kind of rewrite it in the exponential form. Any questions? A little different than yesterday. Yesterday was a little more straightforward. So we are going to graph a couple of graphs yet. So if you flip it over. Again, by hand. We don't need a calculator. So it says the graph of y equals log base b of x is shown below. The first one is when b is greater than 1, because that's our growth function. Anytime b is greater than 1, the graph grows. The second one is for when b is between 0 and 1. That's our decay function. And if you look at the graphs, you can see the left one grows, the right one decays, it goes down. Because y equals log base b of x and y equals b to the x are inverse functions, the graph of the log is a reflection of the graph of the exponent over the line y equals x. That's how graphs work when you're looking at the graphs of an inverse and a regular function. So this function right here, the one on the left, that's our exponential function. That was the growth function that you graphed last week. You graphed one on the quiz on Tuesday. It grows. It starts at the x-axis, it goes up. To get the log, literally you're taking this and flipping it, kind of making it curve in the opposite direction and do the pretty much exact opposite. So if it was skimming along the x-axis and we're switching the x and the y, it's now skimming along the y-axis. It's still growing. It still goes up. It just grows with a different curve. So the curve is like the opposite curve. So right here, that guy there is our log function. So here is our log. So the exponent should be the one that you recognize because that's the one we've seen. So it starts on the x-axis, it goes up. It flips for the log for its inverse, and the log function is the one on the right side. So looking at the decay graph for an exponent is again the one that is like starting higher. So it starts up here, it skims along the x-axis. So it's going along the x-axis. That's what happens with the exponential function. The log graph is the other one. So it's skimming along the y-axis, but it's still going down. So it's starting next to the y-axis, it's starting up high, and then it's going to go down. So underneath this, it says, notice that the y-axis is a vertical asymptote. That's something that we'll really talk about next chapter. But an asymptote is kind of like a vertical wall. It's a barrier. The graph will not go through that barrier. It's not going to touch it. It's not going to cross it. It can't go over it as well. So it can't hop over the wall. That's what this here, why this is just skimming and kind of just going down. Because of that asymptote. And we'll talk more about that later. But like an asymptote is, it's like a brick wall. You can't walk through the wall. You can't touch the wall because it has electricity in it. Whatever you want to say. The domain of the log function. So if you look at this log graph here, what does it look like the domain of that function is? Think from left to right. What does it look like the domain would be? David? 0 to infinity. David, what does it look like the range is going from the bottom to the top? Negative infinity to positive infinity. If you think back to the exponential function and its domain and range, it's the exact opposite of the log. Because if x and y are switching, then my domain and range also have to switch. So the exponential function, the domain was always negative infinity to positive infinity. The range was always 0 to infinity. So they're just kind of switching. Questions? Okay, so let's see if we can graph a couple. The first one says we have y equals log base 2 of x. And I said we're graphing these without a calculator, and they're actually pretty easy to graph if you can graph the exponential function. So if I have log base 2 of x, its exponential function is 2 to the x. So you just take your base, you place it with the exponent, and that's the exponential equation. So whatever the base is, that base gets the exponent to become an exponential function. So we're going to use the inverse to help us graph the log. What would 2 to the negative 2 be if I'm filling out this t-chart? What is 2 to the negative 2, Sam? 1/4. So Sam, 2 to the negative 1 is?
2 to the negative 1?
Mm-hmm.
Half.
Yep.
And 1. And 2. And 4.
Yep. So he said 1/2, then 1, then 2, then 4. Just plugging in those exponents. Pretty straightforward. How can I use this t-chart? You're not graphing it. But how can I use that t-chart to help us find the correct values for the log graph? Virginia? Yeah. So you take the ordered pairs that you found for the exponent, because that's pretty easy to find, and you switch the x and the y. That's the process of finding an inverse that we just talked about to get that inverse equation. So you're going to take x and y, and you're going to flip them. So y is now 1/4, x is negative 2. So the biggest thing to remember about inverses is that in order to find them, you need to switch x and y. Inverses are opposites. So if I'm finding opposites, I have to take the x and make it y, take the y and make it flip to x. These are our new points for the log graph. These are the values that will create our graph. So if you just plot them, x is now 1/4, you're going down to negative 2. And then 1/2, we're at 1, and and so on. So this graph should skim along the y-axis. So start down below, make it be close to the y-axis, and then start connecting those points into a curve. But it shouldn't go over the y-axis. It shouldn't touch it. I mean, it's going to get really close, but it should never go through it. So start low and just connect your points up high. So Caitlin, what's the domain of this graph?
0
Good. And the range?
to negative infinity.
Awesome. We're going to graph one more, but like that's the way that you graph these. You're going to graph the exponent, or sorry, you're going to find the exponent, flip them, and then graph those new flipped points because those are really the points for your log graph. So I'm going to skip the one to the right and have us go down underneath to the last problem here. So that problem says log base 3 and then x minus 1. I want you to, for now, ignore the minus 1 and the plus 2. Just pretend they're not there. This is going to have a translation in the graph. So what would the exponent equation be that we're going to look at to try and find values for? H? 3x. So 3 to the x. Make yourself a t-chart for y equals 3 to the x. Just like we did for y equals 2 to the x. And it should be a pretty basic equation because it's just a power, like a number to a power. You've got a base to a power. We're not worrying about the minus 1 and the plus 2. We're going to take these points and flip them. So I now want the log equation. So this is for my log base 3 of x. Ordered pairs, just flip. There's no math involved. You're just switching x and y. And we're going to graph them. So we're graphing these 5 ordered pairs. If you want to just count by ones, that's fine. You don't have to count by twos. You can just make it a 1. It's just the 1 point we'll put on the graph, which is okay. So the first one is at 1/9 down to negative 2. So technically my last point is going to be off the graph if you count by ones. We're going to dash this just like we did with exponents. I'm going to come back and now look at the rest of my graph, or the rest of the equation. How does this graph translate? So using what you know about translations, Caitlin, how does it move?
It goes up 1 and 2.
You're so close.
Yeah.
So it goes up 2 and right 1. So this part here still moves it to the right. The plus 2 still moves it up 2. So we're going to take our points. Right 1, up 2. Right 1, up 2. And if we wanted to graph that last one, we could. So start down below. So I just took my point, moved it right and up. Took another point, moved it right and up, and so on. The range will be negative infinity to positive infinity, but the domain changes. Sarah, what does it change to?
Would it be 1, 2?
Right, now it's 1 to infinity. And that's the h value. That number in the parentheses now is what's making this domain change. Questions? So again, homework tonight, no calculator. So no calculator for the homework. 43 is writing the inverse equation. So you're given a log, you're going to write the inverse. 51 is a graphing equation similar to this one. 51, and then Virginia, 43.
Oh my god. Dude, all I saw was your leg and then I heard, oh my god.